Okay, so as we start section 4.4, we're going to get into a section in which we are going to apply what we've learned over the last few sections about finding maxes and mins. And we apply them in situations, or in other words, we are doing story problems. Here's a very typical story problem. Find two numbers whose sum is 20 and whose product is maximized. 10 and 10?
Yeah.
Prove it.
10 plus 10 is 20, and 10 times 10 is 100. That's a pretty big number. So.
Okay, so what I want is something a little bit more rigorous. All right?
Do derivatives. Yeah.
All right? How do we prove when we've reached a maximum or a minimum? We prove it by saying that we have a derivative that has a critical point and that the derivative has changed from positive to negative, the first derivative test. So in this case, I'm going to say I have two numbers. X is my first number. Y is my second number. And I want to talk about the relationship between X and Y. That relationship is that X plus Y is equal to 20. I'm going to call this the relationship step. I have to do something that tries to tie together the relationship between my two variables. And if I wanted to make a Facebook joke here, I would say it's complicated. All right. Now, the next step is to write an expression that we're trying to maximize or minimize. By the way, the general expression for maximizing and minimize is that we're optimizing. Sometimes we're trying to optimize it by getting a max. That's typically what we do for things like profits. Sometimes we're trying to minimize something, like costs. All right? So, my next step is talking about the fact that we are trying to find a product. So I'll call it P. P is a function of X and Y. And we find the product of X and Y by multiplying those two together. We'll call this the function step. Our next step is to get our function to be a function not of two variables, but rather of one variable. I don't want a function of X and Y. I don't want my product to be of X and Y. I want my function to be a single variable function. And I do that by combining my function step with my relationship step. Is there some way I might be able to do a substitution? Is there some way that I can replace every occurrence of X with something or every occurrence of Y with something? Lucy, save me. Okay, which one do you want to solve for, Lucy? Okay, X is equal to 20 minus Y, which means that I can take every occurrence of X in my function step and replace it with 20 minus Y. And now my function is no longer a product of two variables or a function of two variables. It's a function of only one variable. So, product is now a function of one variable. It's 20y minus y squared. And if I want to find a maximum or a minimum for the product, how do we find maximum and minimums? We take the derivative, we find critical points, we try to find places where the derivative changes sign. So, from here, Okay, by the way, we'll call this step that we just did the substitution step.
Ooh.
Okay? Our next step, let's take the derivative. P prime of y is equal to 20 minus 2y. Alex is like, I see my answer coming, and he's right.
Yes.
When does 20 minus 2y equal 0? When y is equal to 10.
And then you plug that. You plug.
If I look at P prime, and I put 10 here, P prime, when I'm less than 10,
Positive.
like 0. P prime when I'm greater than 10. That means P must have a local maximum at 10. Okay? Okay, this step here, if we numbered our steps, what? 1, 2, 3. If this, we said, what would step 4 be called? The derivative step. Okay, and then we finish with step 5, which is answer the question. The product is maximized when x equal 10 and y equal 10.
And did you get that x value because you plugged the y that means?
Because I took my 10 from here and I plugged it oops, all the way back into our substitution step. Answer the question. Isn't that great? 5 steps. Relationship step, function step, derivative step, substitution step, derivative, answer the question. Okay? Big idea though is that substitution step gets our function down to a single variable. That single variable function is the one that we can take the derivative of. Are you ready for another question? Here we go.
Mr. Eric, I heard you saw your twin the other day. And,
Yeah, we came up with it.
you looked it up. Don't you guys look like twins? If you had a beard, you would look just like him.
If I had a beard, if I had muscles, if I was black, I think we can make this take. Don't I look a lot like Yao Ming? Except for not being Asian or tall and having hair, I look just like him.
You're right. That's a stretch. That's a stretch.
Oh, stretch. Okay, here we go. New problem. I've got a parabola. That parabola is by definition, wouldn't it be a parabolic parabola?
It's concave out.
This parabola is y is equal to 20 minus x times x. That's a 20. All right? I'm going to inscribe a rectangle in there. so that the top of the rectangle is just touching or on points that are on that parabola. What dimensions for the rectangle maximize the area?
I like it. This is easy. I got it. It's a good problem. I don't know what you think you like it.
Do 5 and 15 are they on the on the parabola? Oh, so certainly. So Stephen says let's just put 5 here and put 15 here and then call it a day.
Yeah. Yeah. Good day. Is that right? Right.
How about?
Wait a minute, is that going through 0, 0?
Yeah, it's supposed to be going through the origin.
Oh.
Yeah.
It's supposed to go through the origin because you can see that this parabola has 2 zeros, one at 20 and one at 0. All right. How can we take this problem?
By making a relationship.
By making a relationship. Okay. I've got a relationship. This point right here is the point x comma y. Oh wait, this point here has the relationship. It's x comma 20 minus x times x, and so is this point here. Well, yeah. Do we want to use x1? I got a great idea. Okay. Let's call this point, I think the book calls it Q. They call this point P. Ready? Let's say point P has the coordinates a comma 20 minus a times a. Let's say Q has the coordinates b comma 20 minus b times b.
Got a smile. He's giggling.
That was more like a cackle.
More like a cackle.
Chuckle.
It's a chuckle.
Because he doesn't have secret.
Yeah, it definitely does.
All right. First of all, let's get rid of these 5 and 15, which were a total guess. All right. So essentially, this is A, and that's B. Can we find a relationship between A and B?
Yeah.
Why not?
Aren't the y values equal?
Both on the x-axis is 0. Because the parabola is not perpendicular.
Go Ian.
So this I could rewrite as 20 minus A times A.
Yes.
Yeah, that's what
Yeah.
Okay.
that way you have a relationship.
Can I look ahead to the area function?
Maybe.
Well, area is length and width. So
The area
So when
is going to be a function of A and B. And area is length, which is that B minus A times
20 minus a times a.
20 minus a times a.
Slope.
All right? Okay, we only need one more thing.
Minus 20 minus 8 times A.
Okay. I'm sorry?
Wait,
No, I mean this describes the area right here, right? Because this is there, and that's
If we want to
there.
maximize area,
all right.
So we are to the point we've written a function. I think we're not quite at. Food's allowed in here as long as it's not a distraction, and I'm getting distracted by that. All right.
Eat it, sorry.
So put it in your mouth, put the bag down, and put the bag away so then I'm not distracted anymore. Okay? We need a step where we get the function of one variable. Right now we still have two variables. We have a and b.
Well, wait. Doesn't b equal 20 minus a times a? Because b is a function.
Is it true that b is equal to 20 minus a?
Times a.
No.
True that.
This is true.
That's insane.
What do we know about parabolas? They're symmetric. So wouldn't the distance here, which I happen to call a, wouldn't it be also the distance here? So the amount I go up is the same as the amount I go down from 20. Does that help? Is that helpful? Sure. That means when we come to the substitution step, we can say every occurrence of b can get replaced by 20 minus a. So 20 minus a times 20 minus a times a. And now function big A is a function of only one variable, little a. I think we need to clean up, expand before we take the derivative. Let's see. 20 minus a minus a. 20 minus 2a. 20 minus a times a. 20a minus a squared. FOIL. 20 times 20a is 400a. 20 times negative a squared is negative 20a squared. Negative a squared negative a times negative a squared is positive a cubed.
Wait, how is it
2a cubed.
Oh, it's in minus a. I'm confused how you got
Wait, I missed a term here. Let's try that again. First, boom, outside, boom, inside, negative 40a squared, okay, and then lastly, plus 2a cubed. Do we have any common terms? Well, first of all, let's get the cubed out in front. Negative 20 and negative 40. Negative 60a squared plus 400a. Okay, so I think we've completed step 3, right? The substitution step.
You can take the derivative maybe.
Step 4, the derivative step. A prime of a is equal to 6a squared minus 120a plus 400. I took the derivative. The derivative of 400a is 400. Okay, so we took the derivative. What else do we do to this derivative? we're looking for zeros. But since we're maximizing, we're not only looking for zeros in the derivative, we're looking for places where the derivative changes from positive to negative. Changes sign and changes from positive to negative. By the way, since this is Harry Potter release day, I've been thinking a lot of the fact that Hermione took a class called arithmancy, which involves looking up a lot of tables. Don't you think we've got it better off having handheld calculators that make it so we don't have to look up things on tables?
Yeah, but
Class is not heavy wand.
Why can't they later on say, I would never calculate?
Solve.
Can they just like solve yourself?
All right. So you have already written down. Right. Minus 120? Is that correct now? Yeah. So there's our derivative function. And what are we interested in about this derivative function? We're interested in where is it equal to 0 and where does it transition from positive to negative? Okay, so we see it positive, we see it negative over here, we see it going through 0 with a transition between positive and negative. How can I find out the value of that value of x on the calculator, but a on our second calc? 0. The left bound, you know what I'm going to do? Instead of using my arrow keys, I'm just going to say 3.9. My right bound, I'm going to call it 4.5. So does it look like the 0 is in between those two bounds?
Yep.
Solve it.
We were off.
Okay, now we use the calculator to solve that quadratic. If I forced you to do it by hand, you would use the quadratic formula. Can you? Does it factor?
Yeah, probably.
I don't. With an answer that looks like that, I don't think it factors.
400.
That's not intersection.
Well, I mean, if I wanted to do intersection, I would have had to say. Oh, sorry. I would have had to say. I would have had to put in a second function. Y equals 0. We did 0. That's exactly what I did. It's second calc. Second calc. Second calc. And I did choose the 0 function. All right. All right. So we found that A is approximately 4.22. I forgot what it was.
4.2264.
6.4? 6.5?
Oh, when it says it's
Wait,
a
six-
parabola.
Wait, hold on. 6.5, which I'll take that to the 7. Okay, now, that's what A is equal to. Now, answer the question.
I was going to say, since it's a parabola, that's the derivative. Wouldn't we have more than 1 0?
Yes, we would.
Yeah, but it's got
Okay, I want you to think about that. Yes, we would have more than 1 0 coming out of this derivative. Hold, let me follow the whole way through. You're going to nail this. Are you going to tell me exactly why there's no contradiction here?
No, I'm not.
Oh, okay. What are you going to say then, Patrick?
Nothing. Never mind.
All right. Ian's correct. The derivatives of parabola. And parabolas either have 1, 2, or 0. Okay? When it has only 1, the parabolas touch and come back. We didn't see that when we looked at the graph, did we?
That's a
This parabola points upward, so what must have happened is that we're looking at this, the parabola comes back up and hits again over there. Do you think that's reasonable?
I like it.
Okay, so yes, there's another place where the derivative is equal to 0. But it doesn't give us an answer. Because what happens here at this other 0? The parabola comes back up, the derivative goes from negative to positive.
Oh, so it'll be the minimum.
It will give us an area that is minimized, not maximized. We're only interested in maximizing the area. So the other answer gives it is indeed a critical value, but it doesn't maximize. Good?
Yeah.
All right. We still have to answer the question. What are the dimensions, please?
How could you get it? Couldn't you just like...
Well, we also have to realize there are a couple of other places that a couple of other places that we would have to look at. For example, this question only makes sense when x or a is bounded between 0 and 10. This other answer occurs where beyond that range. We should also look at what is the area when x is exactly 0. Let me draw that rectangle. It looks like this. If a is exactly 0, how tall is that rectangle? Not infinitely small. It's a very finite number. It's 0. What happens when a is exactly 10? Do you like that rectangle? It's a rectangle that's got a really large height, but a width. Here, go ahead, Nate.
The area doesn't
The area is 0 there too. So only at this spot right here, when that derivative is equal to 0 there, only there is the area maximized. All right. What are the dimensions? Finish the question.
It's like 11.546.
Okay. This dimension here is b minus a.
20 minus A.
The width is 20 minus 2a.
Yeah. It's both sides.
Because we got 20 and then we pinch in a on both sides.
I was going to say that. Okay.
So it's 20 minus 2 times 4.227. And Billy, you said you already calculate that. You said 11.546. 0.546. And what about the height of that rectangle?
66.672.
What's up?
66.672. And how did he get that? He took the value of a and he plugged it into 20 minus he took a and he plugged it back into the original function for the parabola. So make sure you answer the question. You found the value of a that maximizes the area, but that may not be the answer to the question. Yeah, Nate.
Do you think there's anyone that's going to be like this on our homework?
Sure. Oh yeah. Yes.
Don't be that guy.
There's probably going to be like not very many problems though because they're very.
No. That is very true. The number of problems is going down. Are you ready for another one? Yes. Okay, another problem. I do not. I don't.
What's this?
I have Kleenex. This is called optimization problems.
I mean, that's
Modeling and optimization. All right, here we go. This problem is a classic. A classic. This problem reminds me of my father. Nope.
What is that?
This is a problem that reminds me of my father. My father who barely got out of high school, spent his career bending metal. He was a sheet metal worker.
Oh my gosh, it's his culture.
No, he was a sheet metal worker. Sheet metal workers bend flat metal into things like ductwork for airflow. So he was an industrial sheet metal worker, which means if he had let's say you have a factory, a car factory, you have a spray booth where the paint gets sprayed onto the auto parts. Doing that kind of painting requires airflow. You have to build huge ductwork, D-U-C-T, ductwork. That's where duct tape comes from, yeah. All right, to have that airflow. He bent metal into those shapes. Okay, here's a classic problem. I've got a piece of metal that's a flat piece of metal that's 25. Should we do this in inches? Yeah, we'll do this in inches. And it's 20 inches wide that way. I'm going to cut corners out of this rectangular piece, and I'm going to bend those sides up to make a tray, to make a box with an open cover.
We should call your dad and ask him how to do this problem.
I'll tell you a story about that later.
You have to call it.
What dimensions for the box? Actually, no, we won't say what dimensions. We'll say, what is the maximum volume that can be attained by doing this? Okay, are you ready? So what I'm going to do, and my father's he's got snips. I mean, imagine the largest pair of scissors you've ever seen. Okay, where the blades are about the length of my fingers, and the handles are about 1.5 feet long.
So the blades as long as
Except not as sharp. Okay, like Edward Scissorhands. All right. So my dad would take these snips, and these snips are big enough, and the handles are long enough that you can create enough force that you cut through metal, just like scissors cut through paper.
That's pretty cool.
It's very cool.
Long
All right. So by the way, those corners that are going to get cut out, those corners are squares, so that when you fold the corners up. You know what? I'm going to call this dimension here x. And all of these corners are all x by x. Okay? Since I don't have another variable right now, I think we can skip the relationship step. Let's go right to the function step. What is the volume of the box as a function of x?
20 minus 2x.
One dimension is 20 minus 2x. Now why is that? Because indeed the bottom of the tray is going to be this 20 inches, but I took out that x and I took out that x. The bottom of the tray, one dimension is going to be 20 minus 2x. What about the other dimension? 25 minus 2x, and then the third dimension is x. Because the height of it, when I bend that side up, it's going to be x tall. Great. And I don't have to work to make this a function of a single variable because it's already a function of a single variable. So let's go to step 3, the differentiation step. Do you want to clean this up before?
Yeah.
All right. How about we do FOIL on this? 20 times 25 is 500.
Yep.
20 times negative 2 is negative 40x. Negative 2 times 25 is negative 50x. And negative 2x times negative 2x is positive 4x squared. And all of this is getting multiplied by x. So
Why is it all multiplied by x?
Because I have an x here.
Yeah, why is that there?
Because this is, let's call this the width. Let's call that the depth. Let's call that the height. Height. Those are the dimensions of this rectangular box. A rectangular prism. A right parallelopipe. Piped. If I want to break out some more words that describe this three dimensions.
One more.
Right, yeah.
You want more?
It's a box.
Charlie.
All right. 500x minus 90x squared plus 4x cubed. I combine those two terms before I multiply to the end. Paul, is there some sort of medication?
You know that song? Shaggy, it wasn't me.
I have no idea what you're talking
Alright,
about.
I'll say
No, you could. It'll wait. It'll cheat. It'll wait. What?
Jazz.
I listen to calculus music. I'm going to play some for you right now.
I don't like it.
Okay, so we've got past the substitution step. We bypassed that. Let's go to the derivative step. V prime of x is going to equal to 500 minus 180x plus 12x squared. Now, again, we think about this problem as probably having two zeros.
Does 12 divide out by all of those?
It goes here.
No, it doesn't.
It's a 5 times a 5. No, there's no 3's in there. There's no 3's in there. So let's say this time we're actually going to find the exact answer. When does v prime of x equal 0? When x is equal to, let me rewrite this in the order more typically found. Plus 500. We can't take a 2 out of there, can't we?
Yeah.
Can we take a 4 out?
Yeah.
Yeah. So let's take a 4 out. 4 times 3x squared, 45x, and 125, I think. Double check my work, please.
Yes. I like it.
All right, and there's no 3's there, so we can't go anywhere. So x is equal to minus a negative 45 plus or minus the square root of 45 squared minus 4 times 3 times 125 all over 2 times 3. So it's equal to 45 divided by 6 plus or minus the square root. That's going to be huge.
Let's just use
Let's do it. Yeah. Let's do it. 45 squared is 2025.
20, 25. What's 12 times 125?
1500.
1500?
Yeah.
And this is all over 6.
It's actually going to come out with, it's going to be 20. It's going to come out with 25. It comes out to the square root of 525.
You did more than you had to. You can take out another word.
The square root of what?
525.
I mean, like, you could factor out.
It's 575 isn't a.
I know, I was going
Okay, but remember, we get 2 answers out of here. We get 2 answers out of here. I want both of the answers, please. I got 45 over 6 plus square root of 525 over 6, and 45 over 6 minus the square root of 525 over 6.
Well, one of them is 11.319.
11 point what?
319.
319. And the other one is?
67.913.
67. Neither of these answers can be correct.
68.
I got
3.68 is the net minus.
Oh, I didn't divide by 6.
The addition is 11.31.
Okay, and the other one is 3 point what?
681.
681. Okay, I believe we all can look at this answer here and say, bogus. Why? Take a look at our diagram. I've got 20 inches of metal. I'll take 11 inches from this side and another 11 inches from the other side.
It works.
Okay. But could I take 20 inches of metal and take a little over 3.5 inches from both sides?
Yeah.
Sure. There we have it. This has got to be the place. Now, the other thing that backs us up on this is that we knew that this derivative was a parabola. It's a parabola that points upward. And so when we draw that derivative function, its parabola looks like this. Here's where the function switches from positive to negative. So there must be the location of the local maximum. So now, I believe we're to the point. What is the volume? What is the volume that got maximized? The volume is equal to 25 minus 2 times 3.681 times 20 minus 2 times 3.681 and multiply that whole thing by 3.681.
That was the original equation.
It's our original equation with us dropping the value of x into those 3 spots.
How did you pick the big one?
Well, after we solved this quadratic, we evaluated that expression with both a plus and a minus.
820.
Because the other one, the value 11.9, doesn't make sense in the context of this problem. And because that 11.9 wouldn't maximize the volume, it would minimize the volume.
So does that mean that the 45 over 6 is the minimum on the parabola?
No,
Is the
45 over 6 is this value right there.
right? That's what.
Oh yeah, sorry, the minimum value of the parabola.
It's the
Yeah,
x
yes,
value of the.
yes, that is correct. All right.
No, it's not. It's that equal makes it look like-
Any questions?
Oh, the final answer is 820.820.52.
Okay. Okay. Ian's going to say the final answer again, and then I'm going to tell him that he's wrong. Go ahead.
Katie gave it.
Oh. Ian's still going to say it. I'm still going to say Ian's wrong.
Well, I can.
Let's sublimate.
No.
It's
Ian's wrong for copying.
800. I didn't copy everything.
You copied my
and I
answer.
compared
I
answers.
know. But you said you got it too, so we're both wrong.
Slap them both. Make an example.
I got a different number.
820.5.
That's way wrong.
5.
I have another one.
Inches squared.
1059.5.
Is that it? Oh,
Okay. The only reason I didn't know if the number was right or not.
Cute.
It was the matter that the unit wasn't included, but Caitlin said inches cubed, so Caitlin is still more right than you.
Oh yeah.
I
You said
remember
square.
Okay. Okay. So are we still in an argument about what the number is?
No.
According to the book, they have the maximized volume as 820.53, and the units would be inches cubed because it's a volume.
You killed it. Good job, Caleb. That was some nice calculation.
Okay, we'll go out on this last problem. Yeah. Yeah, I'll give you an assignment and then we'll play it out on the okay. the assignment which is in some section is 1 through 49 odd.
He's joking.
50 and then and then 51. Okay, I want you. This is a multi-day. This is a multi-day. This problem set is going to last you all the way through Thanksgiving, the end of Thanksgiving weekend. All right. Okay. This won't be due until after Thanksgiving.
Good deal.
All right. But I need you to battle with these. All right. I really want you to do battle with these over the course of this weekend, and then on Tuesday. No. If you want, you know what? Here's what you do. Here's what we're going to do. Break this assignment into 2 pieces. Let's say you do 1 through 19 odd by Tuesday. All right? And then 21 through 49 is going to be due after Thanksgiving.
That sounds good.
All right?
No, our assignment's really one.
And then of course that part is the AP practice questions. All right? So you got to feel it. So really, let's get at least this much done by Tuesday, and then this will be due really. All right? And in class on Tuesday, the Tuesday that we're here,
Are you checking it?
we're gonna. Yes, I am.
You're killing me, Small. Really?
Also, reference I don't understand.
Have you never seen that?
Fedor.
What movie is it?
No.
No, that's
Number 2.
What?
Okay, obviously we know what movie that's what we should watch on Tuesday.
Okay. So in class, we'll work on those first sets, and I am going to look to see how much progress you put into them. All right?
Mr. Fedor, if I were to Thanksgiving,
You gonna put it in online?
but I actually did it.
What's that?
Can I just bring the homework that I didn't bring today, but I actually like to my last Wednesday?
Okay. You know what?
Or I can bring it to it might be just like
So I have to take off right after class A. So you could show it to me. Know what I'm going to do? Wait, first of all, I don't know why. No, I don't know why you're standing up. Your seat's over here. Your seat's over there. All right. So, I'll tell you what, we're not going to get to that last problem.